screen. I will share my screen. There it is. Come on. There it is. Fabulous. All right. So last time we took what we had learned about the statistical mechanics of distributing quantum mechanical particles into a quantum mechanical system and used that to derive the expected energy distribution of a box of photons. All right, so we worked on a box of photons, and a couple of the defining characteristics of photons is, first of all, they have no mass, so they're massless, so they're immaterial particles, and they also had no chemical potential, so it costs no energy to either emit or absorb a photon. And again, just to, I shouldn't pull things out of my rear, out of the unfortunate possibility that whatever I pull out may not be exactly correct. So just keep in mind that what the chemical potential is it's the energy required to add one particle to your system. Okay, so this is going to again be relevant with what we talk about today. But for photons, again, it doesn't cost any energy to create a photon or emit a photon when an electron, for example, drops down an energy level. It doesn't cost any energy to absorb that thing in order to kick the electron back up. And hence, the chemical potential for a photon is 0. Okay, so now what we're going to do today is essentially the same thing we did on Wednesday, except we are going to do it for massive particles. Okay, in particular, they are not going to have mass 0, and they are not going to have chemical potential equal to 0 either. Okay, so it will cost some amount of energy to add additional particles to your system. All right. But now, before we actually do that, I want to take a little bit of an aside in order to prepare us for the things that we are about to see. All right, so first of all, let me introduce you to a concept called the thermal de Broglie wavelength. Okay, so I will say, but first, the thermal de Broglie wavelength. All right, so let's say we got some particles and we throw them in a box, as we are wont to do. All right, so now typically what you're going to do whenever you have a collection of particles in whatever system it is that you're talking about, you will calculate their partition function. All right, so let's do that. All right, so the partition function in the canonical ensemble, just because that one's easy. So in the canonical ensemble, the momentum partition function. So in other words, so remember you have to sum over all possible states. So there'll be some contribution to the configuration. There'll also be some contribution from the momentum. If we just for the time being focus on the momentum component of the partition function is the following. All right, so we're going to call it Z because it's a partition function. And we're going to put a little p on it just to remind ourselves that this is just the momentum part. All right, so the way that you calculate the partition function in the canonical ensemble is you write down the Boltzmann weight, which is e to the minus beta e. And then this energy in general is going to be some function of the momentum. In particular, if they're free particles, the energy is just going to be the kinetic energy. It's just p squared over 2m, right? Where p squared is just the modulus of the momentum vector. So it's just px squared plus py squared plus pz squared. All right, now to get the momentum partition function, what you have to do is to take this Boltzmann weight and integrate over all possible values of the momenta. All right, so what we're going to do is we're going to integrate. And we have to do 3 integrals because there are 3 components of the momentum. So we will do this. Okay, and again, each of these integrals goes from minus infinity to infinity, so they can have whatever momentum they damn well please. Okay, so now what I'm going to do is I'm going to substitute this in for their energy. So I'm going to assume that they are free particles, as free as the wind blows, as free as the, I don't remember how that old song goes. So again, we're integrating from minus infinity to infinity of e to the minus beta, and then we've got px squared plus py squared plus pz squared over 2m, and then we integrate over px, py, pz. Okay, so we have an exponential of a sum of things in the exponent, and as you guys know, whenever you have a sum of exponents, you can break that up into a product of exponentials. Okay, so we're gonna wind up getting 3 exponentials. So we'll get e to the minus beta px squared over 2m times e to the minus beta py squared over 2m times e to the minus beta pz squared over 2m. And so this part of the integrand only depends upon px. This part of the integrand only depends upon py, and this part of the integrand depends only upon pz. And so what you have essentially are 3 independent integrals that you're just going to wind up multiplying together. And each one of these integrals is just a Gaussian, right? Because it's e to whatever variable you're integrating over squared. So there are 3 Gaussian integrals. Okay, so now being a physicist, one of the tricks you should familiarize yourself with is how to evaluate a Gaussian integral, particularly if you want to become a particle theorist, because the entire job of a particle theorist is to wind up expressing your problem in terms of Gaussian integrals. Okay, but you go look up what how you evaluate a Gaussian integral, and what you will get is this: 2 pi mass times Boltzmann constant times the temperature to the 3/2. So that is the answer. So this is the momentum component of our partition function for free particles. All right, now let's think about this thing. All right, so what do we got here? So let's think about our units. So this is an exponential. That has no units. However, these things are momenta, right? Momentum does have units. So this thing, whatever it is we just calculated here, is going to have units. So the units of this thing are the units of momentum cubed, right? Because we got 3 components of the momentum. Each one of those things has units of momentum. So the final answer is going to have units of momentum cubed. That suggests that we can define something which I will call PT, okay? And this is kind of like, you can think of it kind of like an average momentum, all right? And so what this thing is we're just going to take this momentum component of our partition function that we just calculated here that has units of momentum, and we're going to take the cube root of it so that it has units of momentum instead of momentum cubed. Okay, and so if we do that, this comes out to be 2 pi m kbt square root. Okay, so this is what I would call, so you can't call it the average momentum because we didn't explicitly calculate an average, right? But it is something like an average, right? So I'm going to call this a characteristic momentum. So this is kind of, you know, so you got a bunch of particles that are bouncing around at some temperature T. at that temperature, again, kind of on average, you can expect those particles to have a momentum that looks like this. All right. So now we know from quantum mechanics that if a particle has momentum, it also has a wavelength, right? So our good Frenchman buddy Louis de Broglie showed us that if a particle has momentum p, you can associate a wavelength with that that is just lambda is equal to Planck's constant divided by p. Okay, so if we think of this, it's called the thermal moment, characteristic thermal momentum. All right, so in other words, this characteristic thermal momentum also corresponds to some characteristic wavelength. Okay, and so what this characteristic wavelength is, you just plug that formula in up there, and this is h over 2 pi m kBt square root. And then just to be thorough, because it shows up so frequently, we can also express this in terms of h bar instead of h. Okay, so another way you can express this is 2 pi h bar squared over m kBt square root. All right. And again, all I did here was I took this and then substituted in h bar and then wrote it in a nicer fashion. Okay, so each particle in quantum mechanics is associated with some wavelength, okay? And so again, in quantum mechanics, you can roughly think of the wavelength as being characteristic of the size of that particle, whatever the hell that means, all right? So in other words, you can think of this thermal, so this is the thermal de Broglie wavelength. And what it says is you specify for me what the temperature is. And again, kind of on average at that temperature, particles will have a wavelength that looks like this. Okay, so again, this is something like the expected size. That's not how you spell expected. Expected size, which I will put in quotation marks, of a quantum particle at temperature T. Okay, so in other words, you got a box full of particles. Okay, so here's my box. I got a bunch of particles in there. From a quantum viewpoint, these particles are not points, right? So if you zoom in on this thing, that particle is not a point. It has some size, and that, at least quantum mechanically, you can think of the size as being on the order of that thermal de Broglie wavelength. So this distance here, the wavelength of that particle is lambda t. Okay, so again, what I just drew here was a box full of particles, right? And these particles are separated by some distance, right? Okay, now, so the particles have some density, or equivalently, each particle you can think of as occupying some amount of volume. Okay, so if I say this box has volume V, then each particle has a volume V over N essentially to itself. All right, so in other words, each particle you can think of as, you take the volume, you throw in N particles, and then you can think of those particles as being arranged on a regular grid. And within that regular grid, each particle essentially has this volume V over N to itself. So that's kind of like a volume unit cell per particle in this box. Does that make sense? Okay, so now, okay, so what I have here is each particle has its like unit volume cell that it occupies. Okay, and again, if I think of the particles as being arranged in a regular grid, then the dimensions of this unit cell, I'm going to call that little L. All right. So essentially the volume each particle has to itself okay, which again looks like this. I've got a three-dimensional volume, and the particle essentially sits in the middle of this thing. And so the volume of this little box is V over N. And if I imagine this is a cube, that essentially tells me what these dimensions of my unit cell are. Okay, so in other words, this density defines a length scale, L, that is V over N to the 1/3. Okay, does that make sense? All right, so now what you might expect to happen, again, what we did up here was we said each particle has some finite size that is characterized by the thermal de Broglie wavelength. Now, when that length scale that corresponds to the size of the particle becomes on the same order of the length scale separating each particle in the box, then what's going to start happening is that essentially the wavelengths of each particle are going to start to overlap with one another. All right, so you might expect that when L, which again is equal to V over N to the 1/3, is on the same order of size as our thermal wavelength, that is when you might expect quantum effects to start becoming very obvious. All right, and again, this is 2 pi h bar squared over, oh shit, where did it go? M KBT, right there. Okay. And again, this is, so now what I have is that the scale on which quantum mechanical effects become apparent is given by this. All right. Oh, hey, look at this. This thing looks a lot like a density, right? So it's like an inverse density, right? Density is number of particles per volume. So this is like an inverse density. So now what I'm going to do is just take this expression and flip it upside down. All right, so I get a density, number of particles per unit volume, is equal to m kBt over 2 pi h bar squared. And again, the thermal wavelength has a power of 1/2, and then I raise that to the 3rd power, and I get 3/2. So I'm going to give this its own symbol, NQ. This is what's referred to as the quantum concentration. Okay, so you take a bunch of particles, they have some concentration or some density. And if you start adding more particles or you start shrinking the volume of the box such that the density of the particles goes up, this quantum concentration is the density at which you will expect quantum effects to manifest themselves. Okay, does that make sense? All right, so now this has been a very rough argument. And so now what we're going to do is to make this argument more rigorously. And I'm going to show you that the answer that we get for when quantum mechanical effects actually appear is very close to this, but there is a small correction factor. All right, but I just wanted to introduce this idea of the thermal de Broglie wavelength, which gives the size of the particles. And then that size of the particles gives some expected volume and therefore concentration of particles where you will expect quantum mechanical effects to occur. All right, so now we're okay with the idea of quantum concentration, and that comes from this idea of thermal de Broglie wavelength. All right, so now that we've got that polished off, now let's do the main event. Are you ready to rumble? So we are now going to discuss Bose-Einstein condensation. All right, and what I'm going to show you is that Bose-Einstein condensation occurs just about at that quantum concentration, again, with a little bit of a correction factor. All right, so again, we're going to do exactly the same problem we did on Wednesday. We have a box of dimensions big L, which specifies a volume V, which is big L cubed. And into this box, we are going to throw particles. There they are. Okay, now again, whereas what we did on Wednesday was we talked in detail about what happened when these particles were massless and zero chemical potential, that is photons. Today we're going to see what happens when they have mass, that is, they are material particles. Okay, so just out of simplicity, let's assume our particles have the following properties. So first of all, they are bosons. Okay, in other words, they obey Bose-Einstein statistics. We are going to assume they have mass m. Okay, we are going to assume that they are non-relativistic. And that allows us to employ the Schrodinger equation and the wave function solutions of the Schrodinger equation. As before, they are also non-interacting. So it's an ideal quantum gas. And last but not least, they are spin zero. Okay, so in other words, for every state, we don't have to keep track of, like last time we had to worry about the fact, oh, there's two polarization states, and with electrons, we would have to worry about, oh, there's different spin states. So by assuming they're spin zero, it just simplifies this consideration of how many possible states are there. Well, there's just how many possible momentum and configuration states there are. We don't have to worry about different spin states. You can include the spin states. It would make the math marginally harder, but the answer will still be more or less the same. Okay, now the fact that they have mass m and they are non-relativistic and they are non-interacting, that means that when we solve the Schrodinger equation, what we are going to get is that they have energies that are equal to p squared over 2m. Okay, where the momentum operator, as we all know, is this. Okay, and so now that is the Hamiltonian for these particles. There is no potential because, again, we have no potential in the box. They're not interacting with one another, so you don't have to worry about the potential. So this is the Hamiltonian. Okay, so that makes solving the Schrodinger equation very easy. And what you get, again, as we talked about on Wednesday, is that the energy states wind up being equal to this. Nx squared plus ny squared plus nz squared. Okay, where nx, ny, and nz are integers. All right, so again, basic quantum mechanics. All right, and again, so these are the wave functions of our individual particles. We're going to put these particles into this box of volume V equals L cubed. As before, what we're interested in are all the states that have the same energy, that is, that lie upon a sphere in our K space. Right, so we have a sphere with constant radius K, and all the states that live on that sphere are states that are accessible to us at a given energy. Okay, and again, just exactly as we've talked about on Wednesday, The difference now is that our available states now form a regular grid, which I'm not going to try to draw in any detail. And what we showed on Wednesday is that the density, I don't want to use that, the density of points in this grid we showed on Wednesday is equal to V over 2 pi cubed, like so. And then if we express this instead of in terms of K, in terms of the momentum, that just introduces a factor of H, right? Because again, the de Broglie wavelength, lambda is H bar K, right? And then lambda is related to the momentum. Okay, so we can express this in terms of the momentum, or in momentum space, like this. All right, so this is the density of points on our grid in momentum space. Okay, so we are again going to make the assumption that our box is very big. Okay, if our box is very big, right here, that means that the spacing between these points on our grid is very, very fine, and we can make the approximation that our grid is continuous. Okay, well, what is that? Oh, that's from earlier. What's that still doing there? Okay, so we're going to make the continuum approximation. Okay, and the continuum approximation is that such that the number of states in a volume of width dE is, so again, what we're going to do is kick our shell out by some amount so that we can calculate a volume. All right, we're going to say this thing has width dE. And this, again, by definition, so what I'm doing now is defining the density of states. So the density of states, G of E dE, this is defined to be the number of states in a shell of width dE. So that statement there defines what I mean by G of E. And this is equal to the surface area of my sphere this sphere specifically, times the thickness of the shell when I kick it out by an amount dE, like so. Well, so I don't want to write it like that. I'll say by width of sphere. Okay, times the density of points in my grid. All right, so in other words, this quantity here, this is dV, that's the volume in the phase space that I'm talking about. And then this is my density of points in the grid. So I take the density of points times the volume, that gives me the number of states. Okay, so everybody's cool at this point, I hope. Any questions? We're good? Yeah, again, this is, we've done all this before. All right, so now I'm going to write this in the following way, G of E. So my surface area of my sphere is 4 pi P squared. So again, P is related to K just by a factor of H bar. So whether I'm in K space or P space, it's more or less the same thing. Times the thickness in my P space, dP, times the density of points in my grid, which we just showed up above is V over 2 pi H bar cubed. All right, so now the only problem is that all these things are expressed in terms of P on the right-hand side, and I want it in terms of energy on the left-hand side. So now what I have to do is rewrite this in terms of energy. So I'm gonna, before I do anything with this first, let me just rewrite the first term. The second term, I'm gonna do the same trick we did on Wednesday. I'm just gonna use the chain rule. All right, so dP, I can rewrite as dP dE dE. Okay, and my density of grid points is still just V over 2 pi h bar cubed. All right, so now I need to figure out what to do with this and what this is. But that's pretty easy to do because, again, all these things are free particles. And so the energy of my particles is just P squared over 2m. All right, so this tells me that P is equal to the square root of 2me. So that allows me to replace that with something that is expressed in terms of energy. And if I take the differential of this thing, dP dE, that is mass over P, which gives me m over 2e. So this is dP dE. So I take this and I stick it in right there. All right, and so what I get is my density of states times differential of energy is equal to 4 pi times 2me. So that's my first term. My second term is m over 2e square root times dE. And my last thing is unaffected. It's just 2 pi h bar cubed. Okay, and then algebraic massage. You make this look pretty, and what you get is this: V m to the 3/2 over root 2 pi squared h bar cubed square root of energy dE. So this is my density of states. All right, so that's my density of states. Now what I want to know is how many particles do I have in my system? Okay, so the average number of particles is just equal to the average occupation of each energy level times the density of states of each energy level integrated over all energies. Okay, so that will allow me to calculate what the average total number of particles in my system is. Okay, so now we can all see where this is going. This is going to be our Bose-Einstein distribution. All right, so we take this thing we just derived for our density of states, and we plug that in here. We take the Bose-Einstein distribution and we plug it in here for the average occupation of each energy level, and then we integrate over all energies. Okay, makes sense, yes? All right, now let's take, again, a little bit of an aside to talk a little bit more about the properties of the Bose-Einstein distribution. All right, so aside. Now remember, the way that we got the Bose-Einstein distribution was that we evaluated a sum that looked like this: e to the minus beta epsilon alpha minus mu in alpha summed over in alpha goes from 0 to infinity. All right, so this is where the Bose-Einstein distribution came from, was we evaluated this sum in order to calculate our partition function. Okay, and then we use that partition function to evaluate the average number of particles. And so what we said was that for these set of occupation values for bosons, that what this thing comes out looking like is a geometric sum. And in fact, we know how to evaluate a geometric sum. We said it was equal to this, e to the minus beta epsilon alpha minus mu, like so. All right. Now, there's a problem. The problem is this equal sign is only true under a certain set of circumstances. Okay, so this sum does not always converge. All right, this sum only converges if E alpha is greater than mu, right? So if this exponent here comes out to be, well, this epsilon alpha minus mu, if that comes out to be negative, that makes the whole exponent positive, and then this sum does not converge. That is, you cannot say that this sum is equal to this nice compact expression. All right, so the Bose-Einstein distribution only applies for systems in which all of your energy levels have energies that are higher than the chemical potential. All right, so the Bose-Einstein distribution only valid if your lowest energy value, which is the ground state, is higher than the chemical potential. Okay, and what this looks like graphically. Okay, so on the x-axis, I put my energy. On the y-axis, I plot the Bose-Einstein distribution. There's again the special value of mu. Okay. And what this function looks like is like this. Essentially, it asymptotically approaches mu. So you can fill up states. So over here, these states to the right of mu are allowed, but everything over here is forbidden. You cannot have energies in your system that are lower than the chemical potential. All right. Does that make sense? Okay, so now let's imagine what happens. Let's say that we got our system that's filled up with bosons. It's got some chemical potential. And at that chemical potential, so at chemical potential mu, that will give us some steady state average occupation of our system, average of it. Okay, now I ask, what happens if I stuff in more particles? So I got my nice steady state average number of particles in. Now I'm going to come over and I'm going to jam another particle in there. Okay, so that raises the energy of the system. It raises it by an amount mu. Okay, and in particular, now if I come in and I try to jam in another particle, it's going to be even harder, right? So in other words, as N goes up, so does the chemical potential, right? So the chemical potential sets the average number of particles. If I increase the average number of particles by forcing them in, that increases the chemical potential. Does that make sense? Okay, so if I add more particles, then that's going to raise the chemical potential. And now what's going to happen is if you add in enough particles, eventually you're going to raise your chemical potential to the point. So let's say on my little plot I drew here, let's say that the ground state is, say, right here. Okay, if I stuff in enough particles, eventually what's going to happen is that the chemical potential comes up to meet the ground state energy of the system. And when that happens, this sum up here goes completely bonkers. Okay, does that make sense? Okay, so you increase the number, you increase the number of particles, that is the density. You increase the density, and at some point your sum goes completely nuts. It diverges. Okay, so you raise mu, and what happens is sum diverges. This is Bose-Einstein condensation. So when the sum diverges, that is Bose-Einstein condensation. Okay. All right, so now let's go back to this thing we were calculating right here. All right, so now what we're going to do is let's write it again. So we calculate average of n is equal to integral n alpha. No, that's not what I want. N e, let's put it like that. G of e dE, and we're going to integrate this again. We're going to integrate up to infinity, but in general, you know, you're not talking about weird systems. In general, your lower limit here is going to be some energy that is greater than the chemical potential. Okay, and so what this is going to look like is again, let me just substitute in the Bose-Einstein distribution. Epsilon minus mu minus 1 dE goes from epsilon greater than mu to infinity. Okay, so now the weird thing about this is that even though our sum up here that we use to derive the Bose-Einstein distribution diverges when mu becomes equal to epsilon, this integral does not. This integral still is well behaved. All right, so what we're going to do is we're going to see what does this integral give us? What is the number of particles that will fit in our system when our lower bound here is equal to the chemical potential? Okay, and that number of particles will be the number of particles at which our system Bose-Einstein condenses. Okay, and so now what I'm going to do is I'm just going to shift my limits. So I'm going to rewrite this thing the following way: G of e to the beta epsilon minus 1 dE. And then I integrate from 0 to infinity. So again, all I'm doing is just shifting my lower limit from mu to 0. And by doing that, I'm eliminating the mu here. It's all I'm doing is just changing variable. I just shift my variable over by mu. All right, and that just makes the math cleaner. All right, so let's calculate it. So we have an expression for G of E. Let's plug that in. All right, so when we do that, we get, this is V m to the 3/2 over square root of 2 pi squared h bar cubed. Our integral goes from 0 to infinity dE square root of e over e to the beta e minus 1. Okay, so that's what we got to do now. Okay, now let me again rearrange some things. So let me rewrite. All I'm going to do is just rearrange numbers. Okay, so let me write this in the following way. Squared to the 3/2 times 2 over square root of pi. And then you're going to ask me, where does this mkbt come from? Well, so where that comes from is I'm again going to change variables. So I'm going to rewrite this in terms of a variable called z. Okay, where z is defined to be beta e. Okay, so I make this change of variables. When I do that, this factor of beta comes out here in the front, right? So I wind up with this. Well, holy crap, that is our friend that we just learned about at the beginning of the lecture. This is this thing right here, mkbt over 2 pi h bar squared. This is 1 over the thermal wavelength cubed. Okay, so that mess of constants is essentially our thermal wavelength. This is our volume, easy enough. This thing, let's talk about this. 2 over root pi. Seems innocuous enough. You go show that to your mathematician friends, and your mathematician friends will say, hey, I've seen that before. This is equal to 1 over the factorial of 1/2. And again, you can express factorials of fractions in terms of what's called the gamma function. So this is the, turns out is equal to this. So 2 over root pi is 1 over the gamma function evaluated at 3/2. Okay, so let's now plug all this back into what we have. So we have 2 over root pi integral from 0 to infinity of z to the 1/2 over e to the z minus 1 dz. I can rewrite this as 1 over gamma evaluated at 3/2 integral from 0 to infinity. And then I'm going to say this is z to the 3/2 minus 1 e to the z minus 1 dz. So I'm just playing math games here. And now again, you take this and you show it to your mathematician friends, and they'll say, holy crap, I know that function. I've seen this function before. This is the definition of what's called the Riemann zeta function. Okay, so this thing here is the same thing as, now I find zeta difficult to draw. There, that's zeta. So your mathematician friend will tell you that this is Riemann zeta function evaluated at 3/2. Okay, so what we get is that the average number of particles that fill up our system at the point where the chemical potential matches the ground state energy of our system, that is when the thing Bose-Einstein condenses, is equal to the volume, all right, that's coming from here, times the thermal wavelength to the -3 power times the zeta function 3/2. Okay, and then this, so now what I can do is just divide by the volume, and I get that the average number of particles divided by the volume, which now this is a density, right? I get that this is a zeta function at 3/2 divided by lambda t cubed, and 1 over lambda t cubed, that's our old friend, the quantum concentration, right? So this is zeta of 3/2 times the quantum concentration. So once you hit the quantum concentration times a little bit of a correction factor, that is the density at which your system is going to Bose-Einstein condense. And this is about 2.612 particles per de Broglie volume, where again, the de Broglie volume is the volume of this cube that we said each particle has to itself. All right, I'm almost done. I'm 1 minute over, but I'm almost finished. So now, typically, this is not how you do it, right? You don't have a system at fixed temperature and you add in particles. Instead, what you do is you keep the number of particles fixed and you lower the temperature. Okay, so now this quantum concentration has a temperature in it, right? If you go back, you look at what our definition of the quantum concentration is. Where is it? Geez, that was a while ago. Okay, so right here, the quantum concentration has a temperature in it. All right, so now what you do is you take this expression and you plug it back into our formula down here for when the thing Bose-Einstein condenses, and you simply just invert the thing to get the temperature. Right, so you just solve this for the temperature. So this is going to be some critical temperature at which the system Bose-Einstein condenses. So you just rearrange this to solve for the temperature, and what you get is 2 pi h bar squared over mkb times n over v zeta 3/2 to the 2/3. So this is the temperature where if you have a gas of bosons, that gas of bosons will Bose-Einstein condense. And you can go compare this to a table of things, for example, like helium-4, and you will see that it works actually remarkably well. All right, so that's it. 2 minutes over, sorry about that. I hope you don't mind. And so I think I'm done. So does anybody have any questions? All right, cool. Then we're done. You got 8 minutes to turn in your homework. So I'll let you go now, and have a good weekend. I'll see you guys on Monday. Adios.